Hello, everybody, and welcome to our latest CODA webinar. I'm got to say I'm very excited to have this one. It's one I've been looking forward to being able to host for quite a while now. It's absolutely wonderful to have our good friends from SWIPA join us to present some of the amazing research that's going on inside their institution. So our webinar today will be Advancing Research in Well Integrity and Plugging and Abandonment for Decommissioning. I will introduce the speakers in a couple of minutes, but before I get to that, I'll just really give you a quick update, I guess, and for those not familiar with who CODA is, a bit of a rundown on just sort of what it is and what it is that we are doing here. So CODA, we've been around now. We just had our third birthday as an independent organisation yesterday, but we had a year before that from when we were first established. So we've been around now since 2020. We're a not-for-profit organisation working to support the establishment and growth of Australia's decommissioning industry. And in that, a part of that is to really understand where all the really smart work is going on around the world that's highly valued in that decom space, hence the webinar today. In our own space, some of the work that we've done along the journey, because Australia, when you think 4 years ago, was really at that very beginning stage for its decommissioning, we've undertaken a few studies. We released some documents, review of best practice planning and execution for decommissioning. We've done a technology roadmap. We looked at disposal pathways from the recycling side for the decommissioned materials when they come ashore. Shortly after that, we released what we refer to as partner portal, and I imagine a lot of you on this call are dialing from partner companies, so you may already have had the chance to go in and dig around in the partner portal that we've got. We run a 2-day training course twice a year for people to provide an introduction to decommissioning. And then more recently, in the last 12 months or so, we've released a study looking at Western Australia's ports for their capacity to support the decom work. We put out a skills study back in March. And then the more exciting, or maybe the most exciting thing that we've released this year was our forward look ahead. What you can see running on the screen now is an animation of what that look ahead looks like. Essentially, what we've done is captured all of the materials and wells and everything else that's installed across offshore Australia, not just Western Australia, offshore the whole of Australia. We've put that into a Power BI dashboard along with all of the declared or anticipated decommissioning timelines for all of those facilities. So essentially, this dashboard now gives you an incredibly granular one-stop shop if you want to see what's going to happen in the decommissioning space for any kinds of equipment or facilities that are offshore in Australia at the moment. The intent is to update this 2 or 3 times a year, so there's probably going to be an update for this come out in the next couple of weeks. So watch this space. That'll really be an update of timelines, though, more than anything else. What our decommissioning workload looks like. Across the bottom there, you've got the bar charts year by year, and this is done by asset quantity, so it's not necessarily by tonnage and so forth. But we have a very large volume of work that's going to run through until sort of 2036, 2037 on current forecasts. The bars represent the year the work's going to start, so some of these projects will run out for multiple years. So where there's a year where it looks like there isn't anything, really that just means that there are projects that at the moment there isn't anticipated there'll be new projects start during that time period. In the well space, as you see in the middle on the screen there, 740 offshore wells still classed as active. So we've got a lot of work. We've got a lot of work ahead of us here as we go forward. The timeline for those wells is what you can see on this. This is, again, a screenshot from that same database, and it gives you a real sense of just what the time frame is. But over the next 5 to 10 years, we've got a lot of wells work to do in the offshore space across Australia. Plus, of course, onshore, we're a large continent. We've drilled a lot of holes in the ground over the years. There's well over 10,000 wells spread across Australia. These are in all different sorts of conditions. They're in all different states and territories across the country. We are undertaking some work at the moment to progressively start to quantify the onshore well count in a similar way to what I've just shown you for the offshore side as well. So that maybe gives you a little bit of a sense of sort of where we are and who we are and what we've got going on. Given we're going to be talking research, I wanted to just flag this one as well. This is the National Decommissioning Research Initiative. This is a program we run on behalf of the industry. As you'd see on here, it's funded by the industry, by the 6 operators that are listed in there. And this is really undertaking, as it says, independent research to look at the effects of infrastructure in the marine environment. So it's looking at marine connectivity, degradation of materials, and such like. If you're interested in this side of the research space, we recently released a podcast where we interviewed some of the researchers who've done work in this area. If you go onto the NDRI website, you can access all of the publications that they've released through the entire time that NDRI has been running. So I mentioned the partners and the partner portal and so forth along there. We couldn't do what we do. We can't be who we are without the partner network that we've got. And this slide here has just got the logos of. It was current about a month ago. There have been a few more that have signed up since that haven't yet been incorporated into this. But the good people from SWIPA, you'll see their logo in the bottom right of the bottom block on this slide. They are now the people that I'm going to start handing over to present for the rest of the webinar. From a little bit of a housekeeping perspective, top of your screen, you will have a chat and a Q&A buttons. If you've got questions for any of the presenters, the way we'll run this is we'll introduce the presenter. They'll present for 12 to 15 minutes on their work. Then we'll have a break where we can take questions for that presenter. Then we'll move on to the next presenter. So if you've got questions for somebody as they're presenting, please put them in. We'll moderate them, we'll ask the questions, and then we'll move on to the next presenter following from there.
Oh.
Okay, so in order of appearance, I will quickly go through the names here. If you want to read the bios of any of these lovely people that are going to be presenting for us, they are all up there on the registration page that you would have filled in for the webinar. But we're going to hear in order from Harald Linga, who is the director for SWIPA. And then we're going to hear sequentially from Nils, from Hazzaz, from Sissel, and from Victor, who will each present on their own piece of research and work.
So I will give an overview of the activities in SWIPA and just also describing the center, how it is organized prior to the selected result as presented by my colleagues.
Yep.
SWIPA, that's a Center for Research-Based Innovation. It's the main sponsor is the Research Council Norway, but we also have financing support from the 3 operating companies, Aker BP, Equinor, and Harbour Energy.
Yep.
And the R&D partners executing the research is together with SINTEF as host. It's NORSE, IFE, NTNU, and UEIS. So NTNU and University of Stavanger is the universities supporting this and also hosting the PhD candidates and postdocs. It's an 8-year duration center with total budget for the 8 years approximately 200 million Norwegian kroner, and that corresponds to about $20 million.
Yep.
We also do have a lot of industry partners, user partners, in total 28, and that includes all the large service companies, smaller companies, vendors, and also organizations like CODA, and we also have international organizations like Petroleum Technology Association Canada and Net Zero Technology Center in UK. And we also have academic partners for the universities in Brazil, US, and so on. Really, the key task for SWIPA is to, in a way, solve or satisfy the industrial challenges related to no leakage for eternity when it comes to plugging wells. And here we see the traditional setup with reservoir zones and 2 areas, primary and secondary. And how should we do this more costly? That's actually the scientific challenge and the results we want to develop for the industrial innovations. When we established the center and were granted this center, we identified 6 different topics to be evaluated, well integrity topics: sealing properties of barrier materials, placement of barrier material, verification, and also could petroleum wells be reused for storage or disposal. Clearly, P&A tools and operations are very important, and also how to evaluate the results to, in a way, further utilize the results for technology qualification and developing the innovations.
Yep.
So we looked at the industry organization, what is the primary impact towards industry? And for these different topics, we see that we divided it in standards and regulations. A key here is the NORSOC regulation, developed for the Norwegian continental shelf, but referred to globally actually. Some topics refers to the operation itself, and also a third category is the material selection, where we see that includes actually all the 6 topics. So that's a very important aspect of how to further develop new and cost-efficient technologies. We also received the ranking by our user partners from high to low, and we see that in particular sealant properties are regarded as high priority. The same applies to verification and also the evaluation of results, how to further utilize and interpret the results.
Yep.
So clearly material selection is a key issue for all the projects in SWIPA. The work packages are divided into 4. We have the work package 1 and 2, addressing more low technical readiness level, scientific studies, laboratory studies at small and medium scales. And we also have a separate package on upscaling and testing, where we, for some materials and results, test the technologies at a higher scale. So in a sense, work package 1 and 2 is mainly covered by SINTEF and IFE and the universities, whereas work package 3 is carried out essentially by NORS at the Ulreg test site. And we have a special work package on further selecting the results and defining what should be used for further developments. That's a work package 4. As such, SWIPA is a state-funded center. That means we can take the state monies given to the center and direct it into specific technologies or IP technologies for user partners. So a key here is to generate spin-off projects for further elevating the technical readiness level for selected results. So this, in a way, illustrates the family of alternative spin-off projects which can be further elevating the resource towards commercial use. Work package 1 and 2, in a way, it relates to the fundamental understanding of different barrier materials. So we will potentially use the results for innovation, acceptance criteria, new scientific understanding, and utilize this for improving also the present technology. For the upscaling and testing, we investigate the physical and operation scaling effects, comparing the results for as derived at small and medium lab scale. And we utilize the Norwegian P&A laboratories, which is an infrastructure grant given by the Research Council for a range of test facilities also including a P&A research well at large scale. The operators, when joining the center, looked at this center as a key target will be to gain a more scientifically based understanding of what is necessary as a well barrier. That includes safety margins and also look at the barrier elements as a whole, including the formation. So that in a way directs the motivation for joining to gain a more fundamental research within P&A, well barriers and integrity. And also the operators stated that when it comes to innovation-based technologies, clearly the implementation also needs to have a scientific basis and also to, in a way, evaluate the results. So operators also could consider that this could be relevant, or the resources in SWIPA could be relevant for testing and performing quality assurance for new technology developments. So for the ambitions and expectations, to summarize, aims to obtain a scientific understanding of permanent well barriers, allowing for improved well barrier design methodologies. Key parameters will be costs, materials, barrier lengths, and operations. And we have an ambitious target to reduce the cost with 50% for P&A operations, and that also includes revised standards and regulations. So we have got quite some attention. Bloomberg stated when in the first part of the center announced that Norway bets on tech to cut 100 billion North Sea oil well bill. So we have got a lot of attention for this because it's very important for the Norwegian state. It has been estimated to cost 80 billion US dollars to close the 3,000 wells in the years from to 2050. Collaboration is very important for having a success. We have the research partners, which in a way forms the national team in well integrity in Norway. With the 5 R&D partners, we have international collaboration, and we also collaborate with the national and international authorities, the HAVTIL, which is the former Petroleum Safety Association, and the 3 international partners, Net Zero Technology, CODA, and PTAC. So for the SWIPA selected results, we will show now as we go along. We have selected for presentation: robustness testing well barrier materials with Nils, P&A aspects on settled barite by Hazzaz, leakage monitoring by Sissel, and the insight into barrier materials and their placement by Victor. So that summarizes my introduction. Thank you.
Excellent. Thank you very much, Harald. Just as you finished there was a question came in, so I'll ask you that one before I ask you one of the ones that I've got scribbled down here as well. Do you have a work package on repairing deficient barriers, either side tracks or leaking or misfit barriers?
We don't have a specific work package, but we have a lot of testing with new barrier materials which could be used for such a purpose. Yes.
Very good. Excellent. Thank you for that one. While you're talking about new barrier materials, there are lots of alternates out there now, and just what are your thoughts in terms of how SWIPA would work with those and work with the partners around finding really sort of tailor-made solutions with some of those new barrier materials?
We think that can be a vehicle for further utilizing the creativity among the researchers. We have specific know-how on materials and also solutions, not so much operational experience, but I think that the collaboration with the researchers and the industry could be very valuable and give some, let's say, spin-off ideas and push the technology forward.
And is that spin-off piece, you mentioned that as you were going through your presentations there, what is there a role in, what's the role in there for your research and development partners as far as just moving things along the TRL scale, getting them to the point of fully proven and commercialization?
Our role is to be when we, let's say we have reached or produced some very promising results that can be taken over by user partners, but they have to, let's say, typically in Norway, they apply for support from Research Council for innovation projects or demo projects where research partners, one or more of the research partners in SWIPA still have the function as a research partners, but the industry partner then will own the project in a way. So that's the methodology we do in Norway.
Yeah, so that's the commercial path. That's the pathway to commercialization. Then that the industry partner takes that IP as their sort of their end product. Yeah.
Yes, that's correct.
Very good. So my last question then, there haven't been any more coming on the questions thing there. So the requirement for no leakage for eternity in the Norwegian continental shelf, how do you see that driving the innovation and driving the work that you're doing and driving this sort of quest for better and better solutions?
It's a real challenge, of course. So eternity is it's a term which we it's not so easy to define, but that forces us to think in a new way and also look at the surroundings, the formation, how does it interact, not only with the potential utilizing or keeping this casing or removing it. It gives a new aspect. How can we do this safely? That's priority one, and also cost efficient. So clearly, we need to address both new technologies and the regulation, because as you know, the rig cost is our penalty here. So we need to make this in a more efficient and lighter way, in a way.
Yeah. Focus is the mind, eh?
Yeah.
Very good. Excellent. Look, thank you very much for that excellent introduction there, Harald. So we'll next invite Nils Opedal, who is Senior Research Scientist with Syntef. Nils, the screen is yours.
So thanks for the invite. So my name is Nils, and as Harald and Francis' introduction, I will present briefly our testing on well barrier materials. More specifically, this presentation will be towards annular barrier materials, and more specifically again, the robustness towards cyclic exposure and any kinds of failure mechanisms and or damage they might be exhibiting. So I guess Harald presented this slide also, but I'll go briefly through it. The objective of VP1, the Barrier Materials and Integrity Work Package. What we want to do here is more in scientific detail, try to understand more, not only the barrier materials, as in casing, cement and caprock, but also the sealing abilities, which means also the interplay or the interfaces. So we do some of the work on a single material alone, but what is more important for us in most cases is also to have bi or three component systems where we try to look at least the whole wellbore system. For our experience, most materials are impermeable and solid and robust enough, but often it's the interface that will lead to any kinds of failure or problem in a real well. So yeah, we look at the failure mechanism and also the resulting leakage rate. So the potential innovations, or why we're doing this, trying to investigate more in detail so we can give more a fit for purpose design for future wells. Also looking into new materials and new ideas as to how to do well integrity and decommissioning in a better or cheaper way.
Yep.
So again, quick glance at VP1, not go full detail here. We're not going full detail here. We have 5 sub packages. Package 1 deals with isolated cement plug, meaning cement plug inside casing, extra metal testing. Package 1.2 deals with the anomalous barrier materials, and then we have package 1.3, more specific towards soil isolation in shallow gas zones. Package 1.4 deals with bismuth as a new material, and package 1.5 deals with subtle barite to be potentially used as a barrier material. today's presentation will focus more in detail on what we have done and are doing and will do in package 1.2, again, towards the robustness of annually materials.
Yep.
So we have been doing this now, the scientific community, for a few years. So for Sissel Viig, we have been doing this kind of testing for, I think, about 12 years now. So the original motivation and relevance was to investigate more effective cyclic changes of either temperature or pressure for different wells. So it could be for production well, injection, pressure testing, and so on, and for different well types also. So it could be gas storage, production, geothermal, or CCS wells. Different wells that will have more or less different magnitudes of cyclic changes. So that was our motivation for starting this. So the initial objective was, can we recreate cement sheath failure in a laboratory, meaning in a controlled setting? So we should somehow be able to manage this in a laboratory setting. So the first thought process was, how are we going to be able to downscale this to a manageable scale, but still large enough to be somehow relevant? So we took inspiration from a 12.25-inch borehole, a night fiber casing, downscaled down to about 25% or a quarter of its value. That gives us specimen dimensions of an outer rock with a height of 20 centimeter and a diameter of 15 centimeter. You see Thomas holding a specimen there, so that's about the dimension of at least the first test. We have evolved the testing over the years with different cells with different capabilities, but for most of them, they more or less follow the same order of magnitude in medium scale specimens, if you like. So over the years, this testing regime has evolved into a model-based setup where we can examine pressure or temperature cycling from inside the casing. We can examine different rock types. We can examine different annular sealing times. So we don't say cement, but in most cases it is cement, but it doesn't have to be a cement. It can be just a sealant material, if you like. Also, we have and can investigate different casing types and also the effect of standoff inside the borehole. So the figures here show, at least in the central bottom part, shows a cutaway of one of our cells, showing again how the specimen is located inside a cell, enabling us to cure the cement under pressure, for instance. They are also CT transparent, so the wall is made of either aluminum or of carbon fiber, enabling us to visualize them in CT. So the 3D visualization shows an example of what it can look like when you have the red indicates a fracture in the cement sheath, and the purple blue indicates fracture in a surrounding rock. We impose the different either temperature or pressure changes. So for the temperature sake, on the right-hand side, you see a schematic of a copper rod where the sample is placed upon, and the copper rod is placed on a heating cooling plate where we can generate cyclic changes of the temperature ranging from, I think it's between minus 15 degrees Celsius up to 100 and about 110 degrees Celsius. Likewise, for the pressure, we have a pressure shaft or mandrel. I'm not sure what's called in English. Anyway, hydraulically, we're able to manipulate the inner casing pressure, where we can, again, oppose different kinds of cyclic stresses from the inside of the casing. So that was a little bit of what we do with it, a little bit now on what we want to measure, or what we can measure. So again, when we started some years ago, we sat and thought, okay, we can do something with it. We can apply different temperature cycles to our specimens. How can we really measure something? So the two things we started with was acoustic emission and X-ray CT. The acoustic emission is helpful for detecting exactly when a deboning occurs, because we essentially just listen to a sample. So we place different sensors on the outside, apply, for instance, a heating cooling protocol as indicated by the figure, so ramping up or ramping down, and essentially just listening to when we have a more density of small fractures and movement of the specimen. This is a nice feature to be able to exactly pinpoint when things are happening in relation to changes in temperature, but it doesn't really say that much exactly what it looks like and where it is. So that is where the CT comes handy. So we have access to a CT. Before we had a medical CT, now we have our own industrial micro CT. So it's a small photograph, but in the bottom right photograph, you see one of our cells located inside the CT, enabling us to scan specimens under pressure. So the collage of the photographs is just trying to show what it can look like for some of our specimens when we have go from the initial phase and having subsequent higher inner casing pressures, how you can see that the cracks and defects in cement and all the cracks in rock are forming and growing as you have larger inner casing pressures until we have full catastrophic failure at 320 bars pressure differential. For some of the newer tests now, newer cells, we have moved on from acoustic emission and X-ray CT, moved on to using ultrasound pulse echo and pitch catch methods for using more for microannually characterization and detection. And we also perform flow tests or permeability tests on our specimens to quantify the flow rates or leakage rates, if you like. I don't have any photographs indicating the permeability test because the slide was full, so I can move on to the next slide, showing some highlights, some results of what we have over SWIPA, but also over other projects, our understanding of fluid behavior or fluid permeability in the microannually for these kind of specimens. So how to do this? There's a very basic P&ID of the permeability test setup where we have a cell. So we have multiple cells, which we are able to manipulate the confinement pressure, the inner casing pressure, and also the pore pressure. So we can do a magnitude of different things to our cells here. So what we see when we do this kind of test is that the flow paths or the microannually are elastic within a certain range. And when you say flow paths are elastic, it means in essence the materials, cement rock. So, but they are elastic. So that means that, for instance, if you have a mild increase in casing pressure, you can observe a decrease in the flow rate. That is also reproducible when you deplete the pressure. For this kind of testing, where we have rock and cement and casing, so 3 component systems, we have seemingly lower levels of sensitivity from the confinement pressure. So we don't really know why that is yet. So this is quite a new set of testing that we're doing. So it could be due to an additional material that absorbs stress, or it could be due to an additional interface that absorbs stress. Another thing that we haven't studied yet is how will filter cake behave in this kind of scenario. So that means if you have a filter cake at the rock cement interface and you cycle the difference in the confinement pressure while you do a flow test to see how the permeability of your specimen will behave. So an example of why we are investing in this is in general to see how different materials are behaving in terms of cyclic changes to stresses, also how the fluid permeability is behaving for different specimens. And some more applied question, an example could be that an important feature here is that the conditions in your well from the testing or assessment phase will they be similar during the well lifetime? Because maybe you're assessing your phase with a pressure test or leak tests. If the conditions are different later on, it could easily be that you will have a different kind of permeability test than compared to what you have in the initial phase. So it's important to know as much as possible from your well about the material, mechanical properties, and also of any kinds of defects and or interfaces you might have in your well.
Yep.
Moving on a little bit, still on fluid permeability in microannually. So fluids means gas and liquid. We do both kind of testing out of scientific curiosity. So when you say gas, it means in essence nitrogen, and liquid is brine, can also be CO2 brine in some other projects. What we see that behavior and the comparison between nitrogen and brine flow in this kind of narrow microannually is not always straightforward. So the case if you have, for instance, a dry microannually and flowing gas through it is pretty straightforward. But if you have, for instance, a submerged sample with the microannually filled with water and you apply gas through them, the behavior is sometimes a little bit more difficult to understand. So an example of the figure on the right-hand side shows where we have gas being tested through microannually, and you see this kind of, it doesn't really stabilize when you have a differential pressure. The measured flow rate doesn't stabilize. So this kind of seemingly bellow effect when the gas is migrating through a water-filled microannulus. The bottom right graph shows 2 sets of samples or tests, one with a dry sample and gas flow, where you have, as you increase the differential pressure, you see the gas flow is increasing linearly. Same thing when you do the hysteresis test going down again, it follows more or less within the same line. However, if you do the same test for some of the water-filled microannually, you see that you will have an apparent breakthrough at about 8.5 bars, apparent breakthrough of measured gas flow. But when you do the hysteresis test, you see that it follows not the same line. So either you have a gas breakthrough and or you have a microannually that was there, but the test that you had essentially just shows that the water is being squeezed out of the small microannually. Because an example on the top right is a bit small, but in red, sometimes the flow path geometries can be quite complex. So the wellbore relevance of what we take away is that it's important to know the conditions in a well or microannually to understand the flow potential and the behavior.
Yep.
Second to last slide, I think. So when we do mild increase or changes in the casing pressure or the confinement pressure, we see that we have more within an elastic region of microannually size and shape. If we have more drastic or severe casing pressures, we see that we can generate larger fractures in both the cement and also in the rock face. And the fact that we've seen is important there to understand and predict it is the relationship between the rock and cement mechanical properties. So if you have, as indicated by the figure on the top right side, if you have a larger cement rock compressive strength, for instance, you will have a higher probability of having a fracture at a lower pressure, in inner casing pressure. Other important effects, but not as profound as the relationship between mechanical properties, but other effects are also pre-existing defects. So we see from a lot of our tests that if you have a pre-existing defects, then microannular fractures will grow from them. As again, trying to indicate that on the figure on the right-hand side. Eccentricity is also an effect. But it should be noted that some of these, in terms of relevance for the industry, it should be noted that some of these tests have been performed without confinement pressure. So that means that the specimens or the materials will behave differently to what they will be in a wellbore. So when we do a test like this and get results like this, our analysis or our understanding is that this is a, I won't say unrealistic, but unrealistic / absolute worst case scenario. Because for most cement, for most wells, you will not have perhaps pressure difference of 200, 300 bars, or at least you will have a confinement pressure from the surrounding rock in your well. And then, yeah, to summarize, so we have over the years evolved our setups. So we have different kinds of setups investigating different items. We are able to examine the different rock types, different annular sealant types, casing type and standoff, to do this in a controlled laboratory setting where we can do either pressure or temperature cycling tests. It gives us details on how and where cement rock interfaces or materials fails. Also enables us to investigate multiple interfaces and the behavior of the microannually. So this is again relevant for injection, geothermal, gas storage, and or CCS wells. So I'm not sure if I'm over my time slot here, but that was my last slide. So I'll be happy to take any questions.
That was great. Thank you. Thank you, Nils. While the audience has a ponder about what questions they may want to put in, and I'll come back to one that I missed earlier as well, that either you may be able to answer, or maybe Harald would be able to chip in on as well. One question I've got would be, what next? You know, you mentioned in the early part of your presentation there you've been working now for 12 years in this space. I guess where are you seeing the trends? Where are you seeing the sort of the demand for your research going forward?
Yes, the biggest thing, so we have done a lot, but there are a lot of materials in terms of rocks and cement types also, so we haven't really tested everything. So one thing is towards different materials. We would like to fill in a larger catalog or library of different material types in relation to each other. So that is something we would like to look into. Another thing is also the last years where we've been focusing on the implementation of the ultrasound probe. So we have this for quite downscale tests, but we don't have it yet for the you don't see it on the right-hand side here, but in the CT, we have it for a small-scale setup. We are trying to implement it on the large-scale setup, but it's a bit difficult sometimes with larger scales and making a pressure type. So it doesn't work yet, but that is what we want to do testing on both probability and visualization on specimens, while the same getting details on how the ultrasound response is, to be able to learn more on the logging side.
Very good, thank you. And having given people a minute or two to put a question in, we have an interesting one here, at least it looks interesting to me. It's a two-parter, so I'll ask you part one first. Are you able to create scenarios to model downhole formation stress changes on cement sheaths over time? Yep.
Yes, if I understand correctly. So how can I show this then? Yes, so
Yep.
Yes,
Yep.
okay. The specimens look like this. So three components, rock face, cement, and casing. So when we do this testing, again, we haven't done all the different settings. So we're able to manipulate casing pressure, bore pressure, and also confinement pressure. We haven't investigated a lot yet the effect of confinement pressure, but that is something we are looking into now. Again, a library catalog of different materials, yes, but also for the same kind of three component materials, investigate cycling effect of both inner casing and confinement pressure to see how at different pressures a rock behaves in relation to a cement. In essence, the interfaces then. So that is something we are just starting to scratch the surface, but we're looking more into that now to do this kind of testing. So the answer is yes, if I understood the question correctly. So we're starting that now.
Very good. And the second one here is, do your analyses cover future impact of CO2 related activities on legacy cement?
Yes, so we're able to perform permeability or flow testing. That is also something, it's on our to-do list. We're a little bit behind schedule, but it's definitely on our to-do list for the same kind of specimens as talked about here. We can easily shift from nitrogen gas flow to brine CO2 flow through this test to see how self-sealing effects and so on will occur in these kind of test specimens. So this is definitely something that we are going to look into in the... We were hoping to be finalized by this autumn, but in essence, it will mean probably next year. That's how time goes. But yes, we have the capability for these kind of tests, and it's something that we're looking into, yes.
Excellent. Very good. Now, this is a question I missed as I was doing the switchover between Harald and you. So if Harold's still on and with us there, I'll ask this question. If either of you want to have a go at answering this one, or both of you, then that'd be great. And this was, what about the placement challenge to achieve a formation to formation seal?
Yep. You and me first. Okay, can I try first? Because in these smaller setups, it's a little bit difficult with having good placement, because that's something we try to implement, because cement placement, you need, at least to my understanding, relevance a little bit larger scale. So I think in our relatively smaller scales, it would be difficult to do it. But it's something we honestly struggle with, trying to make as relevant as possible specimens is difficult. But now, yeah, Harald, please fill in.
Yep. Yeah, this confinement pressure is clearly an important issue. So I think you have indicated, Nils, in the UCS results, or the impact from UCS for rock versus cement, that this has it's really addressed or impacting the performance of the formation to formation sealability. So still we have some more work to do there, but it's clearly very important, as Nils has indicated in this graph upper right.
Yep, very good. Excellent. Well, thank you very much. Thanks, Harold, for stepping back in. Thank you, Nils, for your presentation and for taking those questions. Okay, so next up then we have Hazzaz Bin Yousuf, who is a PhD candidate at the University of Stavanger. So, Hazzaz, the screen is yours.
I'd like to welcome you to my presentation on the subtle barite as annular barrier, characterization, and refinement, which I am currently doing as my PhD topic, and this is my third year in PhD. So first, I would like to say a little bit about myself. I am currently a PhD candidate at UIS. I've completed my master's in petroleum engineering from NTNU, and then I worked in Chevron for 7 years, and I actually did everything, like as a drilling engineer, onshore, offshore, intervention, drilling, P&A, perforation, rig inspection, acceptance, everything. So after that, I moved to Norway and started my PhD. So let's talk a little bit about our agenda. Here I'll talk about our background, what the type of methodology we are currently using. We'll talk a little bit about our results, a little bit about the potential, how can we use my research in the industry, and what are my deliverables. I hope that you will see something very interesting in my presentation. So firstly, what I'm actually working on. So as you have told us in your presentation that Francis told us in his presentation that there is like 740 wells in Australia that currently in operation and will need to be PN at some time in future. Also in Norway there is like thousands of wells that need to be PN in the future, and this is the ultimate destination of all the wells. And this PNA actually costs a lot of money, and there are different stages of PNA. And one of the stages that costs the most money is called the cut and pull operation, where we have to cut the tubular, we have to pull a little bit up and place our cement. However, sometimes we have seen that when we make the cut and pull our casing, we cannot pull. The reason is the mud behind the casing became solidified, settled, solidified, and so strong that it turns into a barrier, some kind of barrier, and it won't let the casing pipe to be pulled out, which actually ends up in a big NPT and a big headache for the oil field. So my research is very simple. I have to find the reason why it's happening. I have to find a way how can we solve this problem, and also I have to have to see if we can use this as a barrier itself. We like using the problem as the solution to reduce the cost in the PN operation. So as I told you, my plan is very simple. I have to find the reason, I have to find the solution, and I have to find the way to use it. And we believe that there will be different impact. We can actually minimize the risk of operation. We can reduce the time of cut and pull, or if we can turn it into a barrier, we can actually reduce the PNA time, which actually end up with reducing a lot of money, and we will have a new type of barrier. So we started our research in March 2022, and we are kind of lucky because in August 2022, Equinor told us that they have recovered some pipes full of Sissel barite from North Sea, and that actually gives us a big opportunity to look at the real thing and work on it. So we have done a lot of characterization on those materials. We've done a lot of experiments, and after these experiments, we find some interesting results. Firstly, from XRD, we have seen that there is no new phases of barium in this Sissel barite, which actually indicates that the Sissel barite formation process that does not involve any reaction. It is a physical process. And we also see that there is no cementation. The particles are very, very compacted, but they are really strong. And so we actually try to look at the elements, and we found that there is one element that is completely new. It was not in the cuttings. It was not in the drilling fluid as well. The element is iron. We have seen a large amount of iron in this material. So, and then we actually try to do a QM scan to see how the materials are arranged, and we actually seen that this iron is actually creating the bridges between the barite particles, which actually so this actually solves the problem of our first question, solve the answer that maybe iron is the reason that we are having this Sissel barite problem. And because we know that, and there is a lot of research where we found that in the downhole when due to friction, due to running pipes. A lot of iron came from the walls of our casings and the pipes. And we believe that this iron goes in, mixed with the drilling fluid, and destabilizes it, settles it down, and then the compaction, temperature, pressure, and all the other downhole conditions actually make this drilling fluid to settle down, to solidify and create the saddle barite. And you might have some questions like, this kind of iron creation happens in every well. So why we don't see the saddle barite problem in every well? We believe that this iron, the amount of the iron should be higher than a threshold value, or else the saddle barite or this solidified saddle barite will not happen. However, we are currently doing research, further research on that, and we hope that we'll find our answers. So our next job was to find a solution. So the solution of this is to break this saddle barite. If we can break it, then we can circulate, and if we can circulate, we can have formation and pull the casing out. And so we have to find a way to break this saddle barite. So there are two ways. One is if we can take the iron out. If we can take the iron out, we are actually destroying the bridges between the particles, which actually weaken the particles and solve the problem. Or we can go to the barite itself. If we can dissolve a lot of barite, that actually help us to weaken this saddle barite formation. So we tried with gelatin agents, and we found that if we use EDTA in a normal pH, and without any kind of pH modification, it goes and attacks the iron, take the iron out, and it weakens the formation. We also find that if we use EDTA at high pH, like we use for acid job or for barite scale job, it can also weaken the saddle barite formation, and it by dissolving a lot of barium materials. And we also find that the performance actually dependent on the pH, depending on the concentration of the material, and how much how much EDTA or how much we actually use other gelatin agents also, and we found that the whole family of these gelatin agents can work to dissolve the saddle barite or disperse the saddle barite. So this actually kind of like solve our second problem, which is like how can we break this saddle barite. However, gelatin is a solution, but we are still currently working on it because there are some safety issues in using EDTA, and also there are some efficiency issues as well. And number 3 is the hardest part, settlement and make the saddle barite itself. That is, if we can find the recipe which will, when you pump it, it will slowly settle down, compacted and solidified on its own, which can be used as a barrier during the P&A. So we have found in our first research that iron is the reason why the saddle barite formation is happening. So we like to test the effect of not only iron but all the metal ions to see if metal ion itself has this effect or not, or how metal ion affects the standard drilling fluid. And we found some really fascinating results. We have found that the trivalent metal ions, which is both iron and aluminum, destabilizes drilling fluid very quickly in a very small amount. It goes in and destabilizes within minutes if we use some kind of iron salt or aluminum salt. The other monovalent and divalent ions, they don't have that immediate effect. However, if we keep this for like 45 days, as you can see from the chart, the other ions can also destabilize the drilling fluid in a long run. So we can say that the trivalent actually destabilizes very quickly, where the other ones are not that much quick in destabilizing the drilling fluid. So this actually help us to understand that what we're seeing in our Sissel barite, that there is a high amount of iron, and the hypothesis that we are having that iron is the reason of the Sissel barite formation might be right, because iron actually can destabilize the drilling fluid, and it's important not only for PNA or for Sissel barite, but it's also important for our standard drilling operation, because there has been a lot of research on barite sagging, dynamic sagging. However, this iron is actually another important factor that might be contributing to the sagging problem. So, how can we use our research? So, as I tell you, I have 3 objectives in my research: find the reason, find the solution, and find a new barriers. And if I can manage to complete all 3 of them, actually, that actually gives us a lot of potential for industrial use. If we, as we found the reason that iron is responsible for the formation of the Sissel barite, now we know that we have to do a really, really good hole cleaning to prevent the Sissel barite problem. We have to get as much as iron out of the well so that it doesn't go and destabilizes our drilling fluid in the long run. Number 2 is for solution. We found that if we can take out iron or take out barium, we can solve the problem of the Sissel barite. So now we have to find a solution which can satisfy the HES and other standards. A solution that we can use to take out iron from the Sissel barite material. And the problem is not easy to solve, because we are actually pumping something that will take iron inside the iron pipe. So you should understand that this is a little bit complicated problem, but we are currently working on it. And number 3 is if we can use it, or if we can make the barrier by ourselves, make a Sissel barite barrier. And if we can do it, we can actually omit, or we can actually reduce the whole cut and pull operation. I mean, maybe we can then easily PNA every well without doing the cut and pull, or without using a rig for cut and pull operation, which will save a lot of money for PNA. We believe that if we can use Sissel barite as a barrier, we can actually able to save around 40% of the total PNA cost. So, however, we are currently working on it, and we hope that we'll find the way to, use this Sissel barite as a barrier. And finally, deliverables. We have published 2 journal papers in SP. You can see it in here, and we are currently writing out 3rd journal paper, which is on the effect of metal ions on the stability of water-based mud, as I've shown you in the slides. Currently, we are working on the oil-based mud. We are similarly trying to characterize this oil-based Sissel barite, and we are trying to find a solution to disperse the oil-based Sissel barite. And we hope that we will find this. We can show you some results soon. Thank you. This is my last slide. And I welcome the questions.
That was very interesting. Thank you very much, Hazzaz. Just out of curiosity, I mean, you're PhD candidate, so you're quite early in your research career here. How far through your own program are you with this work? Because it seems like an awful lot for you to be doing with your PhD.
This is my 3rd year. So normally in Norway, the PhD is like a 3-year project. So I'm in my last year.
Nearly finished, eh?
Yes.
Yeah. So what next? Similar question to what I asked Nils. What next? Both for if you finish your research, you pass it off to someone else, or do you continue on? And where will the research go next, do you think?
For me, I'd like to continue on this research because there is like a lot of unanswered questions, and which I'm really interested to find answers. And I think this has the potential to really, really reduce the cost of the PN operation. And it could turn something very good in future, I hope.
Yeah. Sounds like you're on a very interesting path there. Do we have any questions from the audience? There hasn't been anything that's come through yet. Oh, here we go. So we got one that's come in here. Thank you, Steve. It says, interesting research. Thanks for the presentation. Does sound promising. Any checks on what the results will look like around chromium casing? So 13 CR or 25 CR as different from carbon steel.
We have planned to check. We are planning to do some test using casing where we put our settled barite recipes in there, and we'll try to see, and we try to compact it and see the pressure test and everything. And we have a plan to check different type of material, different type of casing material, and we want to see the effect of different type of casing material on the settled barite formation.
Yep, very good, excellent. So it's on the list. I think between you and Nils, you've got a very long list of things you want to do next. That's
yes.
That's excellent. So look, there haven't been any more questions come through. Thank you very much for that one, Steve. And if I can now, I'll thank you again, Hazzaz. Thank you. That was very interesting. I'll now hand over, please, to Sissel to give us your presentation. So Sissel is a senior researcher at the Institute of Energy and Technology, IFE, and I believe based in Oslo, so a much colder climate outside the doors than a lot of us are facing at the moment. Over to you. Thank you, Sissel.
Great. So I'm going to give you an overview of the work we have been doing now with tracers for monitoring leakage of plugged wells. So why should we use tracers for monitoring leakage related to PNH? When you're going to plug a well, as we have heard earlier today, it's going basically to last forever. And of course, it's possible to monitor the fluids leaking from the reservoir by itself. But these fluids, you will probably have a natural background of these fluids in your system and the seabed. So you will be able to detect these if you have a big leakage. But if you have a small leakage seeping through your barrier, you will not be able to detect it until you have a big problem. So if you include tracers in your plant system, this tracer will be unique in the environment. And if you detect it at the wellhead, you will know for sure that you have a leakage from your plugged well. In oil and gas operations, tracers are conventionally used for interwell application to characterize the reservoir, to characterize fluid communication and distribution and circulation. And it's also used to evaluate oil saturation in swept volumes. But when it comes to P&A operations, they can be used to monitor fractures, microfractures, or also porous matrix communication between the well, a plugged well, and the seabed, and act as an early warning system. And as I said on the previous slide, because the tracers are unique in your system, they will give you a unique identification of a possible leakage. Also, we have been in our research, we are working on water-based tracers. They are already proved for reservoir applications, and they're relatively cheap to be used. In our work, we have done laboratory experiments, not any real field applications or research, but we see that two possible ways of including tracers in a plugged well. Either the tracers can be embedded in the matrix of the barrier itself, or it can be placed below the barrier, as illustrated on the picture on this slide. So when we select and develop tracers, they have to fulfill certain criteria. When you select possible tracer candidates for your system, you need to know that the tracer is unique in the system it's going to be introduced to. You need to know that you can detect small concentrations or amounts of the tracer. So it's easy to detect even small amounts of the tracer and detect small leakages. Normally, we can analyze down to PPT level of a tracer. They need to be environmentally acceptable, and they have to have a reasonable cost. And when you have some tracer candidates selected based on these criteria, they have to be qualified in the for the system they're going to be studied in. So they need to be stable for the time frame of your test, both when it comes to temperature, chemical stability, and biological stability. It's also important that they don't interact with anything in your system. You don't want it to soak to any surfaces, because this will prevent you from monitoring your tracer. You also need to investigate the dynamic properties, flooding properties of the tracers at the conditions relevant for your system, to know that it's matching the movement of the phase it's supposed to trace. And then, of course, you have the HSE parameters. And for the tracers that we are studying, it's the existing oil and water tracers for oil and gas applications, for reservoir applications. They have been qualified on all these criteria. But then to come to plug and abandonment, the conditions are different. We have different materials. They might interact with the plug material, for example, and this is something that has not been considered. So it's important with future development. Yes, so as I said, we need to know that the tracers that flow through the system that they're going to monitor and don't interact with any surface. And in a plugged well, the barrier material, like cement, they are highly active surfaces, and it's likely that there might be an interaction between the tracer molecules and the cement or other plugging materials. So that's something that's important to investigate. Also, you have assets that are converted into storage sites for CO2 or hydrogen that can possibly impact on the barrier material, but can also influence on the tracer stability itself. So this is something that's important to investigate further. And how do we then work to qualify tracers for P&A operations? We have been doing two different types of experiments so far. And the first type is batch type experiments to study temperature stability and possible sorption characteristic of the tracers together with selected barrier materials. And in our test, we have selected some traditional water tracers and also a couple of oil water partitioning tracers to be included. We have tested 3 different types of plugging materials, 2 types of cements, and 1 geopolymer. And we have exposed our samples to different temperatures from 60 degrees Celsius and up to 120 degrees Celsius. Our tracers have been dissolved in synthetic formation water and then have been exposed to the temperature and the plugging materials for 1, 4, and 8 weeks to look at the stability. And then for the batch experiments, we have 2 sets of experiments. One is purely temperature stability investigation, where the tracers are dissolved in the water, but with no barrier material present. And the other are experiments to study sorption or other interaction between the tracer and the barrier material. And in these experiments, the tracers are dissolved in the water and also crushed barrier material are present to the samples. And they are exposed for up to 8 weeks at the 3 different temperatures. And this slide shows a brief overview of some of our results for the stability and sorption testing. On the left-hand side here, you see results from temperature stability at 90 degrees Celsius, where the tracers are dissolved in synthetic formation water. On the x-axis, you see the exposure time from 1 week and up to 8 weeks. And on the y-axis, you see the recovery. And one is 100% recovery, meaning that the tracers are stable at the tested conditions. So here, no plugging material present. And as you can see, there's no reducing trend observed, suggesting that the tracers are stable for the time frame of the experiment. On the right-hand side here, we see results from some of the experiments where we have introduced plugging materials. Here we see results for tracers exposed to 90 degrees Celsius with geopolymer present. And here we see results for tracers exposed to 90 degrees Celsius with cement class G present. And again, we see the exposure time on the x-axis and the recovery on the y-axis. If you see on these two figures, we have some spread in the results, but we don't see any reduction in the tracer concentrations after 8 weeks. And this indicates that we don't have any interaction between the selected plugging materials and the tracers included in the test. That was the results we have so far from batch experiments. And then we move forward to the second type of experiments that we perform, which is flooding experiments. And in this, to perform these experiments, we're lucky to borrow a cell from one of our research partners in SWIPA North, and you see a picture of it here. It's a barrier cell with a cemented casing with some defects. The cement is Portland cement, and it has some microannular channels and low permeability porous matrix. And to perform the experiments here, we have a pump that's pumping water through the system from this left-hand side, and it's moving through the casing, not produced at the outlet on the right-hand side, and then you can collect samples from the outlet. We did two types of experiments in this one. One was a step injection, and to perform this experiment, we inject the tracer continuously into the fluid flow, and it's moving through the plug, and then it's produced, and we continue the experiment until we reach a stable level of the tracer concentration at the outlet, where the concentration at the outlet matched the concentration in the injected solution. The other type of experiment was a pulse type injection, and here we injected the tracer, a small volume of the tracers as a pulse, which is moving them with the water through the system, and we get a tracer pulse at the outlet. To perform these experiments, we included 8 water tracers and also a reference tracer, tritium-labeled water, which is a radioactive water molecule that is the ideal reference tracer for water. And the aim of the project was both to compare the tracer response curves with ideal water to see if we have a match, and also to see if we can use the tracer response curves to characterize or give information about the plug. So on this slide, you see results from the flooding experiments where we did a step injection. You have the flooded volume on the x-axis and the produced tracer concentration on the y-axis. The dark blue curve here is our reference tracer, tritium-labeled water. And we see that most of our tracers, they follow the same general trend as the reference tracers. These two here on the other side, they clearly have deviation from ideal behavior. It's probably close to reversible sorption to the Portland cement. And if you look further into the curves, what type of information can we gain about the system that it has been flowing through? Well, we see that we have this steep increase in tracer concentration at the beginning before it continues to increase, but with a much slower increase until it reaches a stable level here. And to interpret this, we can say that for this level where we have this steep curve, we probably have a high permeable channel. And here, this slow increase in tracer concentration show that we also have some low permeability zones where the tracer moves through. And I switch to the next slide where you see results from a pulse injection of the tracers. Here we also see that most of the tracers follow the same trend as the ideal reference tracer, except for the two same tracers that we saw on the previous slide that have a deviation from ideal behavior and are retained through the system. Again, we see that a big part of the tracer signal is a steep pulse, a sharp curve, which is the tracers moving through a high permeable channel. And then we have this long tail indicating that it's low permeability zones where the tracer continues to move through for a long time period, even actually after we stopped collecting samples.
Yep.
So to sum up our results, we see that the conventional water tracers, they can be used as a basis for long-term monitoring of wells after permanent P&A operation. But it's a need for studying their interaction with different plugging materials, because we have observed that some of the tracers don't behave as expected or as we wanted, together with some selected materials. It's also a need to develop a sampler or analyzer to be installed in the seabed to continuously monitor possible leakages. And it's a need to develop a deployment method of the tracers within the well. We see that we can gain information about swept volumes, permeability, and porosity from a system, and that this can provide input into development of models about the formation and propagation of fractures in plug materials. And we see that conventional water tracers can be used to evaluate in situ fluid saturation, distribution, and saturation in cemented section of the well, but that it's a need for careful test design.
Yep.
And that was everything from me. Thank you.
That was really interesting. Thank you, Sissel. I was having flashbacks there to the early days in my engineering career when I used to work with chromatographs, and it felt some of the graphs that you were showing on there looked very similar to what we used to see as the gas would flow through the different capillaries. But that's a completely different part of industry, but really, really interesting there. Thank you. While we wait, we have a question. Excellent. That's good. I don't even have to go to my own here. So we've got one here. Interesting use for tracers to monitor P&A wells, but they have relatively short life, 10 years max, I believe. Won't this limit their use in P&A wells where leaks may take years to develop? Do you have any thoughts on that?
When it comes to the stability of these tracers, one of the reasons we started to look into the conventional water tracers that have been used for reservoir application is that we know that they have a long stability in reservoir. If you do a interval tracer injection in an offshore region, you might take years before it goes through, and then it even also circulates because of re-injection. And we know that we can continue to detect the tracers for a really long period. So our experience is that these tracers for reservoir application have long stability, and then also should be useful for this. But of course, it's always and needs, as I said, for careful test design to look at the stability at the correct conditions and how to deploy them and how you will actually be able to monitor it. Yeah.
Careful selection of the right materials. Very good.
Yes.
No, that was great. Thank you. So I guess there's a question here that probably lies to that one anyway. In the batch experiments you presented, you showed that the stability for over 8 weeks. That presumably that showed that they really were stable over that time period, and running the test any longer wouldn't have been beneficial. Is that right?
Yeah, normally you start to see a reduce if you have degradation or an interaction with the material. You start to see it quite early. So if you have a stable trend for 8 weeks, then most probably you will continue to have a stable and yes, that's good.
Wonderful.
We have previously also done some experiments that I didn't present here that we were running for so longer time that you can't run an experiment for 10 years, for example, to look at the stability. So
No. Very good. While we've been talking, another question has come in, so we'll do this one and then we'll hand over to the next presenter. So Steve, who should get a prize for asking more questions than anyone else, has been very good here. Is there any plan for research in other media in a situation where there are a considerable number of wells potentially with low pressure and low volume methane emission, which manage to bypass the cement barrier before it gels up? Do you see potential application for, say, methane tracers or other isotropic tracers to help in this area?
Yes, I will say so. So we just had to start somewhere, and then we started with the water tracers. Yeah, but it's possible, and we're up for good suggestions that we can include in our work for different tracers, also to monitor to have typical gas tracers that could be included there.
Brilliant. Thank you. Thank you very much for that, Sissel. That was really, really interesting. Very, very interesting. It's interesting as well looking at the chat here. There's actually conversations going on in there as well. So people are asking questions and other people are commenting. It's it's very interesting to watch. Okay, so over to number 4, please, Victor. If you'd like to take to the screen and present us on your work.
So hello everyone. As presented before, I'm Victor Lima. I'm postdoctoral fellow at the University of Stavanger, and today I'm going to talk about insights into barrier materials and their placement. I want to start first talking about, or at least highlighting that we are going to see in this presentation that the work packages in SWIPA are nicely interconnected, and we are going to see this in this presentation here. So this map that Harald presented in the very first presentation today, showing the WP1 and 2 with the small and medium scale, and WP3 with large scale, and how these should feed each other. It's true, and I'm going to show some of these interconnections. So when it comes to the background and motivation of all for the results that I'm going to present today, I highlight here just 2 points: the de-risking barrier material placement by monitoring density and rheological properties with inline measurements, and also improving the understanding of barrier verifications using tracer gas, contributing to the roadmap for the new P&A technologies. So starting with the placement of the barrier materials and how we should address the viscosity, or how we should track the rheology of the slurry before the placement. So nowadays, the way that we address this topic is by sampling a amount of slurry and then going to a rotary viscometer, doing some ramp up and ramp down of RPM, at the same time doing some dial readings, that is basically some torque measurements, then converting the RPM and the torque measurements into shear rate and shear stress. Then this is basically the flow curve that you have that represents the behavior of your cement slurry. However, this is a manual process, is prone to human error, and takes time. So when we initiate this placement project inside SWIPA, the idea was to propose something that we could do the measurement inline while we were mixing and conditioning the slurry. So we proposed the use of pipe viscometer, where we had a set of DP sensor 1.5 meters apart. Also a Coriolis flow meter, where we could have a flow measurement and also density measurement. Also a screw pump. This screw pump is a very good feature because we can ensure that we have the flow without any pulsation effects. So we can ensure that you have this smooth curve when reading the flow measurement and also the DP, and also a temperature sensor. So we can make sure that all the variations that we can read when it comes to pressure variations is related to temperature rather than variations into the slurry properties by itself. So this the setup is connected in parallel to a batch mixer, as you can see here, and this it's used to run the sequences, where we can grab the raw data, and the raw data is basically the one that we can see up here. That is the flow and the DP through time, and this flow rate and DP through time we can easily convert to shear stress and shear rate using some calculations. So the latest operation that we used, this pipe viscometer, it was a commissioning test in the North PA labs. So this is the first point that I want to highlight. So this North PA labs is the Norwegian P&A laboratories that Harald mentioned before. This is an infrastructure project, as Harald mentioned. This is led by Harald, and this commissioning test, it was a test that we did using the U8 well, and this U8 well it's placed in the UHIG test center, and in this commissioning test we use an offshore style batch mixer, and we connected the pipe viscometer setup to this offshore style batch mixer. So the idea was to mix a large amount of slurry, then do some sequences using the pipe viscometer and check if the pipe viscometer could really fit to this type of setup, and if we could really do the measurements while doing the mixing and doing the conditioning of the slurry in that case. So here are some of the results that we got by that time. So the open symbols, the open hole symbols over here are the data that we got from the pipe viscometer measurements. You can see that we have some dispersions over here. This is because the equation that we used to grab these points, it was a derivative equation. That's why we have these small deviations, these small noise, let's say like this. But if you look at the Herschel-Berkeley fit to it, that is this continuous line, you can see that you have a very good fit to the data. Then when you go to the field symbols, the green, blue, and black, gray one, that are the ones that represents the measurements that we got from the FUN 35 measurements, that it's the rotary viscometer measurements. You still can see a very good agreement between the two instruments. And finally, the dashed line is the Herschel-Berkeley fit to the FUN 35 measurements. So in this first graph, we have the 3 sequences that we did in the pipe viscometer all together. Then we separated the 3 measurements into single curves, as you can see in the right-hand side. And here it's clearer that we still have a very nice agreement between both instruments, and also between the hydrological models and the data that we got.
Yep.
However, until we reach this stage where we could attach the pipe viscometer to the batch mixer, to a full-scale batch mixer, we had a very long way where we tested different polymeric fluids, water, different scales, like very small scales. We increase the scales, we test different cement paste, and we also tested different alternative barrier materials. So by that time, we wanted to make sure that the pipe viscometer could do the readings, could have very good agreement between a conventional way of doing the measurements and the new way of doing the measurements, the inline way of doing the measurements. And this could match without any impact or effect caused by the type of the material that we used. And as you can see, once again, over here in these curves, we still have a very nice agreement between the pipe viscometer and the FUN 35 measurements when we compare the pipe viscometer and the rotary viscometer. I want just to highlight before I move from this slide that if you go to this mid graph and also to this right-hand side graph, we can see that we have a range that we have like this gray part of the pipe viscometer curves, like over here and here, and also this part over here in the geopolymer. This range is a range where the flow was not fully developed when we reached the DP sensor region. And this is connected to the type of geometry that we used for the pipe viscometer. So this is not a limitation of the concept of the pipe viscometer, but it's a limitation of the geometry that we decided to use. So this is easy to overcome, and this is further addressed in one of the papers that we published. So I'm gonna show these papers later on. So if you have any questions, or if you want to learn a little bit more on that, it's a way to do it. So the second point that I want to mention, the second research point that I want to address in this presentation is this fluid flow through fracture surfaces. That is the tracer gas activity. And for this, what we did, it was to create a section. This is a 1 meter section. And then for this 1 meter section, we had a 9/5/8" setup with a 7-inch casing inner. Then we cement a annular, and we applied 150 bar inner tubing while curing. And then after 1 week curing, we relieved the pressure, and then we created a debonded region between the inner casing, the 7-inch casing, and the cement sheath. So in this region over here, between the inner casing and the cement sheath, we create this debonded region that is basically the fracture surface, the microgranules.
Yeah.
So this is the object of study that I'm going to address in this part of the research. Then we started to build up the setup, and the setup is basically an inlet where we attach it a Windum pump where we can displace water, and also a gas system where we can displace the gas. The gas was a nitrogen gas. At the outlet, we had this bubble catcher with a weight balance. So we could detect the amount of water that was passing through the outlet. And also the bubble catcher was relieving the gas. And the gas that was going out over here, it was passing through some flow meters and also gas Coriolis. So basically, we had full control of everything that was coming in and also everything that was coming out.
Yep.
And over than that, we also had this pneumatic pump that was connected into the inner casing. And by changing the pressure of the inner casing, we could play with the microgranular size of this fracture surface. So we could have different sizes of microgranules over there. Then we started to characterize the cell. We started by doing single phase measurements. And in these single phase measurements, we played with no tubing pressure, and we found an hydraulic aperture that is the microgranular size of 40 microns. We applied 50 bar pressure and found around 30 micrometers microgranular size. Applied 100 and 150 and so on, and then we had this behavior. And we applied both gas and water seepage gas test. And this point is also connected to what Nils said in his presentation. So the point here is that when we performed the gas test, we did just after the curing process, and the gas, then the cell was basically almost in dry conditions. So it could have a very close behavior between the gas seepage and the water seepage. Then when we go to the two-phase flow test, then we saturate the cell with water and we do the gas seepage. Then we can see what Nils also talked about, that by that point, we start to see that we do not have the direct microgranular size that we measured before in the single phase measurements, but then we have an effective microgranular size. And by the time that we increase the gas pressure over there, we tend to this asymptote, and then we reach this actual or real microgranular size that is the one that we measure in the single phase measurements. So we did it. With these measurements, we could do some models approach to calculate the relative permeability, like Brooks and Corey model and Van models. But the main idea of this approach, it was to reach the tracer activities or try to correlate the time to breakthrough to the microannulus size. That is also somehow connected to what Sissel presented. So it was the next point, the last point of this research. So what we did, in this last part, instead of building up the gas pressure while having the cell saturated with water, we saturate the cell, we applied a constant gas pressure, and we wait until we detect the gas breakthrough. And by having the time to gas breakthrough and the total gas that we injected in the system, we could calculate the microannulus size of the system. But the way that we did it, we calculate the effective microannulus size instead of the absolute one. That's why it was very important to do the previous steps that we did to address the single and to address the two-phase flow. It was based on the two-phase flow and the relative permeabilities that we calculate in this step that you could really do the corrections that it was needed over here and to do this very nice estimative of the microannulus size based on the time to breakthrough when displacing the gas. So when it comes to the potential for industrial use, I would say 2 points over here: placement methodologies, operational procedures for cementing and remediation, and also the insights into barrier material integrity, allowing for a more comprehensive evaluation of barrier effectiveness and identification of potential weaknesses using tracer tests. And when it comes to the follow-up, I know that 12-15 minutes, it's a small amount of time to really dig into these details of this research. But I mean, if you would like to go further in these results, you can either contact or go through these papers that we already published. If you want to have more details into the pipe viscometry, you can go to this paper, for instance, pipe viscometer for continuous viscosity, is the one that contains the details related to the design and also most of the contents related to the cement paste and also the alternative barrier materials that we tested. And also, if you want to check this single and two-phase test that we did, and also this time to breakthrough approach that we use to try to evaluate and also to estimate the microannulus size and permeability of the 1 meter cell, we can go to this annular cement shift characterization and hydraulic aperture assessment. So I hope that I was clear enough in this time. And I'll be glad to answer any questions that you may have. Thank you so much.
That was excellent. Thank you, Victor. That sort of pulled together a couple of the threads from the earlier presenters as well. So it was nice to have that one placed at the end there. Again, we have overrun a little bit, but those that are still on, if you have any questions, please do put them in. I've got one that I'll ask you while everyone's having a consideration. What are the limitations of the breakthrough time model for predicting the microannulus size in the current stage, please?
Yeah. So I think that the main limitation over here is still the point that we should know the relative permeability when applying the model that we are using in this current stage. And more than that, we only addressed until now the case where we have the cell saturated with water. We have the plan to change the viscosity of the existing fluid in the next stages. So this is another thing that we want to check, how the viscosity of the existing fluid can impact these estimations. So so we should first check how these parameters can affect, and also try to find a way to do not depend a lot on the relative permeability, at least at first.
Yep. Very good. So look, in the interest of time, I will call it there. I want to thank firstly our 5 presenters, so Harald, Nils, Hazzaz, Sissel, and Victor for taking time out of your days to share some of this really interesting work that you've been doing with us. For those of you on the call, thank you very much for joining us, and thanks for putting your questions in where you've had them. For the recording, for those who watched to this point, if you want to reach out to any of the researchers, we will share some information at the end of this, and we'll put it up on the email that will go out to everybody as well. Whether you were able to attend or not, if you registered, you'll get an email with a link to it. There will be a recording of this available on YouTube in the next 48 hours or so you can watch it with your family and friends, on these nice, long, relaxing Christmas holiday evenings. Sit and watch the research that's being done in this fascinating space here. And on that, look, have a great end of the year, everybody. And yes, thanks everybody for joining us. Thank you.